Assalamualaikum, my name is Amina and I'll be the first one to start our presentation about Rubiadin. So this is the mass spectrum of Rubiadin, since the y-axis refers to the abundance and the x-axis refers to the mass to charge ratio. So as you can see here, the tallest peak or the most abundant peak is at 254.1 mass to charge ratio. This peak corresponds to the molecular ion of the compound, which the molecule lose one electron. This gives the molecular weight of the compound. So in this case for Rubiadin, if the molecular ion peak is at 254.1 to mass to charge ratio, this indicates the molecular weight of the compound as well is 254.1. When Rubiadin is being analyzed for the mass spectrum, the lower peaks are recorded as well, which refers to the fragmentation peaks of the compound because they arise from the breakdown of the molecule due to the unstable energy during the ionization process. Meanwhile, the larger peaks might represent diamonds or other related fragmentation. So fragmentation peaks provide insight into the structural components of the Rubiadin, which helps to elucidate its fragmentation patterns during ionization. So based on our previous explanation about heteronuclear matrix quantum correlation, we can say that it's the structure of CH3 because the F1 chemical shift records 7 parts per million, meanwhile the after chemical shift records 2.2 parts per million. Next, we can say that it's carbon number 4 because the F1 chemical shift records 107 parts per million and the after chemical shift records 7.39 parts per million. And we can say that it's the carbon of 5 and 8 because the F1 chemical shift records 127 parts per million and the F2 chemical shift records 8.24 parts per million. And lastly, we can say that it's carbon number 6 and 7 because they have a very close off spectrum in the chemical shift. F1 chemical shift records 134 parts per million and the F2 chemical shift records 7.93 parts per million. Lastly, we talk about the heteronuclear multi-bond correlation, which detects the long-range coupling between the proton and carbon through 3 bonds away with great sensitivity. In HMBC, we can use the quantum probe, which shows the correlation between different protons and environment in the molecule. As you can see here, the peak at 2.196 ppm with the chemical shift at 162.49 suggests the interaction of the methyl group coupling with the carbon number 3 with germinal coupling 2J.
And secondly, the peak at 118 ppm. It suggests that the interaction of CH3 will attach to the carbon number 4, which refers to the 3J coupling, which is a vicinal coupling.
The next part is for the proton NMR. It is 1H NMR spectroscopy. We have to read the spectrum from the right side. The first one is 2CH3 peak, which is the methyl group. We get the 2.2058 ppm, and then the next one is 1OH that we get from the left side of the spectrum, which is 13.2413 ppm. Here we cannot recognize the 3OH peak because due to the chemical equivalence, they will give rise to only one peak because they will experience the same magnetic environment and have the same chemical shift. Next, peak value for 1H NMR. The first one is H4 at the value of 7.3890, and then for the value H6 and H7, we get the range between the 7.9062 until 7.9464, and then for the H5, we get the range of 8.2194 until 8.2495, and then for the H8, we get 8.3016 until 8.3310 ppm. While some peaks appear at multiple rather than single peak because of coupling, which is arises from the interaction between neighboring protons. And then next is carbon-13 NMR. Here we have to use the HMBC, which is heteronuclear multiple bond correlation. It is the detect long range of coupling between proton and carbon with 2 or 3 bonds away. Other than that, it detects the indirectly quaternary carbons coupled to protons. Here we get to see that 2CH3 peak, we get 7.3165, and then we get the value of C3, C4, C5, C6, C7, C8, C9, C10, C12, C13, C14, and 2CH3 in the correlation table. Here we get to see that carbonate is at the C9 and C10. Here we have recognized that C9 and C10 is a carbonate. How we recognize that C9 is greater than C10 on the chemical shift? Because C9 has a higher shielding effect, which is electronegativity is higher at C9 rather than C10. hence the higher chemical shift. After that, the carbon NMR for the next part is using the HNQC method, which is the heteronuclear multiple quantum coherence. This involves the analysis of correlation between proton and directly bonded heteroatoms, scalar coupling, typically carbons within a molecule. Here we recognize that C4 is at peak 107.1731 and then C14 at 117.9426, and then for the C9 and C8 is very similar, which is 126.7538 and C8 at 126.4792, and then we get C12 at 132.3813 ppm, C13 at 133.5395. C6 and C7 is very similar at 134.2577 ppm, while C7 is 134.2432 ppm, because the carbon position or the coupling is very near to each other.
And so lastly, we can say that the large proton signal refers to the cross coupling, and the diagonal represents individual proton signals, while the cross peaks indicate the spatial interaction between the different protons.